Welcome to Hart und Trocken. My name is Dirk Schiborn, and in this video I want to talk about the most important rule for differentiating functions, the so-called power rule. In our last video we have discussed a construction method for the derivative of a function. This method calculates the derivative at a given point a as the slope of the tangent to the function f at this point a. As the slope of this tangent cannot be calculated directly, it is calculated as the limit of the slopes of a sequence of other lines, so-called secants. A secant is a straight line which goes through 2 points on the curve. First, the point in question, which is a f of a, and second, some point which is further right, which is a plus h, f a plus h. If we now let tend h to 0, the sequence of the secants converges to the tangent. Accordingly, the sequence of the slopes of the secants converge to the slope of the tangent. The slope of a secant is calculated by means of the slope triangle, and the slope of the secant is given as the quotient of the vertical leg divided by the horizontal leg of the slope triangle. This quotient is called the different quotient, and you see that the slope of this specific secant is 2.75. If we now let h tend to 0, the slopes tend to the slope of the tangent. You see it goes down, it goes down, it goes down, and it will probably approach 2. However, in the limit we have a problem, because there's a 0 in the denominator and we can't calculate the slope anymore. This is why we replace h by a 0 sequence and use techniques to find limits of sequences. This is done by this calculation, and the result of this calculation is that the limit of the tangent at point a equals 1 is 2. So we have found that the slope of the tangent to the function f at point a equals 1 is 2. In other words, we have found that the derivative of f at a equals 1 is 2. Now, of course, we want to have the value of the derivative for any point a, not just for a equals 1. This process creates the derivative function as a function of the value a, or we can also call it x, along the x-axis. That means we want to move that point a along the x-axis. And we can do that. You see how the tangent changes, and you also see how the limit calculation changes. So in this case, at point 0.5, we find that the slope of the tangent, or the derivative of the function f, is 1. And we can go further to the left and watch what happens to the tangent slope. And as we approach 0, you see that the tangent gets horizontal and the derivative is 0. And we can even go further to the left, where you see that the tangent slope gets negative. Negative slope, negative derivative. Now this is all very nice, but to be honest, we don't want to play through this procedure for any given point a we want to calculate the derivative for. So we hope that there's some way of a shortcut. Ideally that we are given the function, in this case fx equals x squared, and we can write down the derivative function without having to play through this procedure again and again. And in fact that is possible. You probably know many rules for differentiating functions, and all of these rules base off these approaches. So it's all about finding general ways to perform these calculations for different categories or types of functions. For instance, like polynomials, rational functions, trigonometric functions, the exponential function, and so on. And once we have generally performed these limit calculations for the different types of functions, we can pack the general results into rules. Rules which don't have to do anything anymore with finding limits of sequences. Rules which make calculating the derivatives of functions as easy as playing solitaire or something. So from now on, it's all about finding these rules for the different types of functions. Let us start with the function we have been looking at in our graphical example, fx equals x squared. Calculating the derivative f prime at x means calculating the limit of the slopes of the secants. We start by replacing f by x squared. That means we have lim h to 0. Now x plus h squared minus x squared divided by h. In the next step, we expand the brackets by applying the first binomial formula, which gives x squared plus 2xh plus h squared minus x squared divided by h. Now the two terms x squared cancel out, and we obtain lim h to 0 2xh plus h squared over h. And now we see that we can reduce the fraction by h. We do this, we get lim h to 0 2x plus h, only one h, over 1. And now we see that h tends to 0 because it's a 0 sequence. And what remains is 2x. Now, what have we found? We found that the first derivative of f equals 2x. So by calculating the limit of the slopes of the secants, we have found the derivative function of f for any value x. Now I want to do the same calculation for the function fx equals x to the third power. So I replace the exponent 2 by 3. Now let's see which parts of this calculation we can keep and which we have to change. Obviously, I have to replace these two exponents by 3. So let's do that. And now I guess the next steps will be pretty different. That's why I'll wipe them out and do the calculations again. So that is equal to lim h to 0. And now what should we do about this expression? It is the term x plus h taken to the third power, which is, when we expand this, x to the third power plus 3x to the second power h plus 3x h to the second power plus h to the third power. And then there's still the minus x to the third power left, divided by h. And now we proceed very similarly as before, lim h to 0, and we see that those two cancel out, which is why we have 3x squared h plus 3xh squared plus h to the third power over h. And now again we reduce by h. Lim h to 0, 3x squared plus 3xh plus h squared over 1. And now again we look for 0 sequences. This is definitely a 0 sequence, and that is also a 0 sequence because x is a fixed number and h goes to 0, so that complete expression goes to 0. So what remains is 3x squared. That is the derivative of x to the third power. Now, mathematicians always want to generalize things. Whenever there is something to generalize, they do it. In our case, we want to generalize the exponent of x. So we replace 2 and 3 by a general natural number p. So we now look at the function f of x equals x to the power of p, where p is some natural number. Now, when doing the limit calculation, things get a little more complicated than before. But let's see how far we get. We have lim h to 0, and now the challenge is what to do with this expression. We have to multiply x plus h p times with itself. In fact, there is a very beautiful pattern of how to expand this expression no matter how big p is. It is based on a generalization of the binomial formula and is very closely related to something which is called Pascal's triangle. However, in this moment, we won't dive deeper into this topic. Rather, there's only one thing I want to point out. Let me show you what I mean. If I want to expand the expression x plus h to the power of p, this expansion starts with x to the power of p plus p times x to the power of p minus 1 times h, followed by some other summons which we don't care about. The only thing we do care about regarding these extra summons is that each summand has a factor of a power of h which is at least 2. So we can say that each summand contains h to the power of q with q greater than or equal to 2. Using this, we can continue with our limit calculation. So I replace x plus h to the power of p by that new expression, which is x to the power of p plus p times x to the power of p minus 1 times h, and now plus dot dot dot. Finally, we subtract x to the power of p, which is the last summand, which is that summand up here. Now we divide that by h. What follows is very closely related to what we did with the power of 2 or 3. First, you observe that the two x to the power of p cancel out. And what remains is lim h to 0 p x to the power of p minus 1 times h plus our famous ... divided by h. Now again, similarly to what we did with the power of 2 or 3, we reduce the fraction by h, such that we have lim h to 0, and now we have p x to the power of p minus 1 without any h plus ... divided by 1. But now it's important to observe that something changed regarding the ... This is why I color them yellow instead of blue. Because reducing by h means that each of the summand which is contained in the ... has lost one factor h. And that means that we now can write each summand contains the factor h to the power of q with q greater than or equal 1 instead of 2, because one factor h has been taken away from each summand. Nevertheless, the important thing is that there is at least one h in each of these summands in the yellow box. That means everything goes to 0 when h goes to 0. And what remains is p x to the power of p minus 1. And that is the derivative of the function fx equals x to the power of p. This rule is probably the most important differentiation rule and is called the power rule. The power rule says that for the function fx equals x to the power of p, the derivative of this function is given by p times x to the power of p minus 1. Expressed in natural language, that means we take the exponent p, put it in front of x, and reduce the original exponent by 1. So for example, if we have fx equals x to the power of 100, we have f prime of x equals 100 times x to the power of 99. So that's it for this video. Thanks for watching and see you next time.